Okay, so welcome back. So today, I mean, we have joined back. So we will finish up the left out part of the casting solidification module. So if you may recall that in the last class I have discussed about the, I mean, several variants of the die casting processes. So now today we will discuss individually about different die casting processes and their merits and also their applications and how they are compared to other casting processes that we have discussed before. So starting with that, so we are, I mean, starting with the die casting. So it involves, I mean, gravity die casting. So it involves the preparation of components by injecting molten metal at high pressure into a metallic die. It is closely related to permanent mold casting in that both the processes use reusable metallic die. Applications are the typical products made by die casting are carburetors, crankcases, magnetos, handlebar, housings. So there are only few parts which are mentioned over here. There are several other parts spanning across several automotive engine components like I mean knuckle housing or connecting rod, even the engine housing, and also several, I mean, some critical aerospace parts and also components relevant to the mining industry, and also more importantly the electronic industry. For example, the heat sinks for several high power LEDs, and also for thermal management of automotive as well as aerospace, as well as I mean several other electronic application. These heat sinks can also be manufactured by die casting route. So the advantages die casting offers is that it is excellent dimensional accuracy which reduces or eliminates secondary machining operations, and smooth cast surfaces where the RA value, I mean surface roughness, is within the range of 1 to 2.5 micrometers, which is indeed inspiring and really good. And it can be also useful to cast thinner walls compared to what we can achieve in case of sand or permanent mold casting. So the we can go even up to 0.75 walls that can be cast successfully in case of die casting processes. Inserts can be cast in, such as threaded inserts, heating elements, and high strength bearing surfaces. It can offer rapid production rates, and it can also offer, because of it, the pressure involved in the solidification process. So that's why we can also get much faster cooling rate, and also because of the pressure there are the mechanical properties also improve significantly. So for the same material, compared to the its sand cast form, we can see at least around 150 to 200 MPa higher UTS, and corresponding increase in YS values. So that is what we can achieve in case of die casting. However, there are some limitations. So the limitations of the die casting, specifically when we are talking about high pressure die casting, is its very high capital cost, and both the casting machines and the dies and related components are very costly as compared to most other casting processes, and the process is limited to high fluidity metals, and casting weights must be between 30 grams to maximum 10 kg. And in the standard die casting process, the final casting may have a small amount of porosity. This prevents any heat treating or welding, because the heat causes the gas in the pores to expand, which causes micro crack formation inside the part, and also exfoliation of the surfaces when it is subjected to the heat treatment post high pressure die casting. Thus a related disadvantage of die casting is that it is only for parts in which softness is acceptable. So parts needing hardening and tempering are not cast in using high pressure die casting route. But although we started with the giving you a glimpse of the high pressure die casting route, which is one of the widely practiced technique of die casting. However, the die casting starts with the concept of gravity die casting, where we actually do not use any external pressure to cast the liquid melt. It is only the gravity and the gravity assisted flow of the liquid melt within the die cavity. That is what we achieve in this case, and we basically do the casting in a permanent metallic mold. So that's why it can offer a much higher surface finish and dimensional tolerance that we can achieve compared to that we can achieve in case of sand casting of the same material, and also because we are using permanent metallic mold, so we can reuse the mold, and we can make a number of cast parts of the without degrading the die properties. So the dies can withstand a long range of casting cycles, and undercuts and cavities can also be incorporated into the component form with the use of sand cores in case of gravity die casting. That means, although we are using the metallic mold, however, we can still make the cores made which are made of sand, and we can also achieve the hollow sections or hollow subsections within the cast part. So, this process gives a much better surface finish than sand casting, as I told you earlier, and also it because of a significantly higher cooling rate that it offers compared to the sand mold. So, we can get much higher fine grain morphology. So, if you recall the the initial solidification lectures of where I have discussed about the concepts of nucleation and growth. So, here the grain size is much finer compared of the if we are talking about the same material which are otherwise getting manufactured cast by sand casting route, because of more number of nuclei becomes active, because even the mold wall serves as heterogeneous nucleation sites to the solidifying melt, and that is why because of higher amount of nuclei formation there is a restriction in their growth, and they because they do not allow each other to grow, because they start impinging on each other, and in the process we get a fine grained microstructure. In case of permanent or gravity die cast state of the same melt, for example, a aluminum alloy, and whereas the same alloy if we are casting in the form of the sand casting. So, we often see big dendrites with significantly bigger primary and secondary arms. So, that is why even not only its mechanical property is inferior compared to the gravity die cast state of the same alloy. Moreover, because there is a long eutectic region that is present in case of within the interdendritic passage. So, that is why even a crack which is gets initiated at the surface, it gets a free way throughout the brittler phase within the alloy. For example, we are talking about aluminum, 7 silicon and 0.3 magnesium alloy. So, we often achieve primary alpha aluminum phase, and we also achieve the secondary eutectic silicon in the cast matrix, cast alloy matrix. So, there you can see that because of it the crack gets a free way. So, the its fracture toughness and also its ductility is much lesser than the its permanent mold gravity die cast state, where because of the fine grain morphology the eutectic also gets distributed in the intergranular spacings, and that is why the crack does not get a free way. Even if a crack initiates, it gets deflected, or it experiences the encounters the much ductile or softer alpha aluminum phase, and because of this crack deflection its ductility and the fracture toughness also goes high. So, this is what you can understand, that just because of the change of the processing, although the melt composition and the chemistry is same, we can basically achieve improved properties by in this case compared to sand cast state. Okay. So, going ahead with the gravity die casting process. So, in this case there are a couple of steps. Number 1 is that the die is heated and then sprayed with a refractory coating and closed, and number 2, molten metal is then manually poured into the die cavity, and although in some cases a machine can be also be used, like there are machines for tilt pouring and at the onset of gravity. But we generally in industrial parlance, so we also do manual pouring in case of gravity die casting process. So, after the solidification is done, the die is opened and the cast parts either removed by hand or by some ejector mechanism, and finally, the scrap, which includes the gate, runners, sprue and flash. So, like we do the fettling in case of sand casting that we have already discussed. So, even in case of permanent metallic mold, in case of gravity die casting, we have to provide the gating and risering arrangements, so that we can effectively cast the object with the desired microstructural characteristics and the mechanical integrity. So, so those parts need to be removed, but nevertheless, because because of its smoother surface finish of the metallic dies, the resistance to flow is much lesser. So, the fluidity of the melt is much higher. So, later on we will discuss that we can even perform semi solid casting in the onset of gravity, if we can effectively design the gating arrangements, and also we can devise a mechanism to preheat the die, so that the melt does not undergo premature solidification within the gating geometry, and it reaches the component cavity, and it becomes useful to develop the components. Okay. So, with this now we are moving to the pressure assisted die casting, and among them, as I told you that there are two main variants. One is hot chamber die casting, another is cold chamber die casting. So, what is basically a hot chamber die casting? So, in this animation you can very well understand the hot chamber die casting process. So, you can see that here the plunger is basically pushing the liquid melt, and then the melt is flowing through this goose neck into the so this is basically the ingate of the cast the component. It serves as a so here it serves as a sprue, and here it serves sprue and ingates, and then it enters into the mold cavity, and thereby we can achieve the continuous production of the parts, because there is a ejection mechanism mounted at the other half of the die. So, because of this ejection mechanism, so here we need not to go for manual ejection. So, there it can be completely automated, and it can give a much higher casting yield, and also we can make cast a number of parts at a much lesser time frame. However, the difficulties associated with this hot chamber die casting process is that see the casting equipment is subjected to very high temperature of the liquid melt for a long period of time, for the entire casting cycle. So, and that causes wear and tear and corrosion to the casting equipment, and that is why the temperature what it can withstand is limited, and that is why the hot chamber die casting process is limited to some low melting alloys like zinc based and sometimes and brass or zinc based alloys, and sometimes aluminum, but mostly some low melting alloys only, like zinc, lead and tin. So, that is why that is the limitation, but otherwise it is a very effective process to achieve complex contour geometries. So, to discuss about some efficacies of the hot chamber die casting process. So, it deals with a goose neck which is used for pumping the liquid melt into the die cavity. Number 2 is the goose neck, which is submerged in the holding furnace containing the molten metal. It is made of grey alloy or ductile iron, or it also can be made of cast steel. A plunger made of alloy cast iron and is hydraulically operated moves up in the gooseneck to uncover the entry port for the entry of the liquid metal into the gooseneck. And so, these are the steps which are shown with the help of this animation over here. So, these steps you can follow. Only I will focus that for materials such as aluminum and brass, their high melting temperatures make it difficult to cast them by hot chamber die casting process, because gooseneck of the hot chamber machine is continuously in contact with the molten metal. That is what I was discussing. So, that is why you need to one need to limit the kind of metals alloys or metals that can be cast using this hot chamber die casting technique. So, so with this we are moving into the cold chamber die casting, which is much more widely utilized die casting technique, pressure die casting technique in the industrial parlance, which is called the cold chamber die casting technique. So, you can see over here that this is the ladling unit which is pouring the melt into the short sleeve. So, this section of the high pressure die casting machine is called as the short sleeve, and so this once the the metered quantity of the liquid melt which is collected from the analogous furnace by this ladling unit, and placed within the short sleeve of the machine, then the plunger gets operational. So, this is basically the plunger, which is basically this is responsible for pushing the liquid metal within the die cavity. So, then it is basically, you can see that it is getting pressed within the die cavity, and this is how the components are made. And post solidifications, even there is auto ejection mechanism with the help of robotic arrangement. So, that can be achieved. So, that is why this, because of the versatility this cold chamber high pressure die casting technique offers, it is a widely practiced technique for automotive and electronic, defense and aerospace functional parts, and most importantly the automotive engine components, where there is no post finishing or machining is expected. They can be very well manufactured in near net shape by high pressure die casting route. So, it is very much popular among light alloys like aluminum and magnesium, but however, it is also being utilized for brass and copper. So, in this case the longevity of the casting equipment is much higher than that of hot chamber die casting, because here the furnace is not analogous with the casting equipment, rather it is a separate entity, separate device, where from the liquid melt is transported into the short sleeve with the help of this ladling unit. That is what I have discussed before, and so this is how the components are being manufactured. And then the same process of high pressure die casting can be done at the onset of vacuum, when the mold vacuum can be created within the mold cavity with the help of appropriate vacuum arrangement pumps. So, what benefit it can bring? It can bring the benefit, like I have discussed before, that high pressure die casting deals with certain problems like micro porosity. So, because of that also, as I told you earlier, that it is very difficult to heat treat the high pressure cold chamber high pressure die cast components. So, the moment we are able to achieve vacuum die casting by achieving vacuum within the mold cavity. So, then this micro porosity problems can be eradicated largely, and immediately it can bring the benefit that the components comes out as sound with sufficient structural integrity. So, it is not only, so vacuum die casting is of course more expensive than conventional cold chamber high pressure die casting, but we employ this when there is along with the shape of the component, also the structural integrity and the soundness of the component is also on demand. So, then in that case we go for vacuum die casting, and we achieve that by nullifying the presence of microporosity, and also also by increasing by facilitating the heat treatability of the developed parts. So, because there is not much porosity in the cast parts, so that is why there is no fear in heat treating them, so that dimensional alteration or the deformation distortion that is otherwise happens during heat treatment of the die cast parts, that can be largely avoided, nullified. So, that can be achieved. So, so this is the vacuum die casting, and then the another variant of die casting series is which deals with low pressure, is called the low pressure die casting. So, you can see this process has some similarity with the gooseneck based hot chamber die casting process. However, this is different. This is different from the kind of pressure it is exerted here, and here another major difference is here there is no plunger is acting over here. It is only the pressure of the gas pressure that is exerted over the liquid melt, which forces it to move through this pipe, that means by capillary mechanism, and but because of the pressure appropriately. So, it is forces it to flow through this pipe, and then it enters into the die cavity, and then thereby we can get the components made. So, a typical example of low pressure die cast part is the wheel hub. So, that that is being developed in automobile industries. So, that can be very well and successfully manufactured with significantly improved microstructure and mechanical properties by low pressure die casting route. So, it has been adopted generally for casting aluminum and magnesium based light alloys. So, in this process the permanent mold and the filling system are placed over the furnace containing the molten alloy as shown here. I mean, so you can connect it with the schematic, and then the compressed gas is used. So, as I explained to you, so this compressed gas is responsible for pressurizing the melt so that it flows through this tube. So, pressure typically range from 0.3 to 1.5 bars to force the molten metal to rise slowly through the ceramic riser tube that is connected with the mold. So, once the mold cavity is completely filled, the pressure in the crucible is removed and the residual metal molten metal in the tube flows back to the crucible. So, after the casting is solidified, the side die opens. So, these are basically the side dies, and then I mean the top die is raised vertically. So, this is the top die which is raised vertically in this direction. So, the side dies are ejected in the lateral direction, and the top die is ejected in the vertical direction, and thereby the component is kept open, and then so it is ejected from the die cavity, and thereby we can achieve the low pressure die cast components. And so, this casting will move with the top die owing to the shrinkage and will be ejected onto a fast transfer tray. So, this is the mechanism how low pressure die casting performs, and a typical example of a component which can be developed by the low pressure die casting route is wheel hub. Okay. So, the advantages of die casting in general: because of the use of the movable cores, it is possible to achieve complex castings in case of die casting than that feasible by permanent mold casting, and very small thicknesses can be easily filled because the liquid metal is injected at high pressure. So, of course, there is higher velocity involved, and that is why it is also a turbulent filling of the liquid melt sometimes happens within the die cavity, and that is also a point of concern in terms of gas absorption. So, I have already discussed with you that how we can completely eradicate the chances of gas absorption, that is if we can create vacuum within the mold cavity, that can be eradicated. A very high production rate can be achieved in case of high pressure die casting. So, in that way it is economical, and also the casting yield is significantly high, and because of the usage of metallic dies we can get very good surface finish, and there is no post finishing machining is required in case of high pressure die cast parts. And of course, because of that we can meet closer dimensional tolerances, and the die has a long life which is in the order of 300,000 pieces for zinc alloys and 150,000 pieces for aluminum alloys, which is considered as relatively good in industrial parlance. And the die casting gives much better mechanical properties due to higher cooling rate. It is exerted during solidification of the melt, and that is why compared to that can be achieved in case of sand casting because of the fine grained skin formed during solidification, and it is very economical for large scale production. So, these are the advantages and limitations, of course, that we have already discussed, that there are chances of microporosity formation, there are lack of heat treatability of the developed component because of the microporosity present, which can cause distortion. And then another important limitation is that the casting size is limited between 1.5 to maximum 10 kg. It can also go below, but not above 10 kg, and this is not suitable for all materials because of the limitations of the die materials. So, normally light alloys like aluminum, magnesium, and with that some other like zinc, which is also low melting alloy, and copper alloys can be die cast. So, the air in the so the dies and machine, and the number 4 is the capital expenditure. So, both the die and the machines are expensive, and therefore, it is considered to be a cost effective and economical process and industrially viable process only when there is mass production of a particular component is involved. However, when we are talking about the design I mean optimization and developing the prototypes to as a proof of concept for a new material or a new component or a new design, then it is always recommended to go for gravity die casting processes. And once the proof of concept is done and mass production is needed, then it can be I mean taken up for high pressure die casting route. So, I mean then we will move to slash casting. It is also a typical casting technique where we can achieve hollow casting. So, what we do in case of slash casting, we basically pour the it is a complicated geometry component that we can manufacture by slash casting route. So, basically we pour the liquid melt within the complicated mold cavity that is shown over here, mold cavity before pouring, and then we after pouring the liquid melt we allow certain time so that a skin is formed, and the moment the skin of the solidified skin, because the solidification starts from wall, because that is the region where from the heat rejection is happening outward from the wall of the casting to be made, and that is why the moment the sufficient thickness of the cast part is achieved, then we basically just invert the mold, and this is how we drain out the remaining melt which is still in the liquid state, still waiting to undergo solidification, and thereafter we eject the mold and then we achieve the final casting. So that is how we can get complex contoured hollow castings by slash casting route, and this is how the thickness of the casting can be determined in case of slash casting based on this equation. The equation it can be expressed as T is equal to C1 root over T s plus C2, where C1 and C2 are the constants which depends upon properties of the castings, the material, also the dimensions, and T s is the solidification time required. The solidification time of a casting T s, which is a function of the volume of a casting and its surface area. So, based on Chorinov's rule, we know that solidification time T s varies as volume by surface area whole square. So, T s is equal to K V by A whole square, where K is the solidification factor and V and A are the volume and surface area of the casting respectively. And so, thereafter we move to the squeeze casting process. So, squeeze casting is also one of the widely used variant of the casting process. So, how they are different from conventional die casting or sand casting process is that we are basically allowing the liquid melt to solidify under the onset of pressure. So, in the squeeze casting process, molten metal is introduced in the die cavity of the metal mold using large gate areas and slow metal velocities to avoid turbulence, and when the cavity got filled, then high pressure in the range of 20 to 175 MPa is imparted and maintained during the subsequent solidification stages, and parts must be designed to directionally solidify towards the gates, and the gates must be sufficiently large that they freeze after solidification in the cavity. So, thereby allowing the pressurized runner to feed additional melt to compensate for the solidification shrinkage the melt undergoes. So, the applications of squeeze casting process it can be mostly applied to again like light metals like aluminum and magnesium castings, and it has also been adapted to the production of metal matrix composites, where the pressurized metal is forced around or through formed or fiber reinforcements that have been positioned in the mold. So, this is how we can achieve the squeeze casting process, and so now here comes the semi solid casting, which is the one of the most advanced technique for that we are discussing now. So, what are the benefits of with the semi solid casting? So, semi solid casting can remove the fundamental difficulties with conventional casting, that is it can completely get rid of dendritic microstructure. It can also avoid the segregation issues, and it can give the compositional homogeneity, and it can also be useful to achieve the thin section castings, although having a globular microstructure, and it also can cause low gas porosity, enabling heat treatable components of the cast parts, and also it facilitates high mechanical properties due to the unique globular microstructural features that can be achieved in case of the cast parts, and also it offers extremely high surface finish. So, I mean semi-solid casting can be broadly classified as high solid fraction slurry based process and low solid fraction slurry based process. So, in high solid fraction slurry based process, we are talking about slurries, I mean semi-solid slurries, where I mean evolving primary solid particles or grains are present within the liquid matrix of that alloy. So, one of the primary prerequisite is that semi-solid processing or semi-solid casting can be mostly done with the alloys. That means, it is the prerequisite to have a freezing range in the material. That means, there must be a solidus temperature and there must be a liquidus temperature and there must be a gap in between them, and solid semi-solid processing or semi-solid casting takes the advantage of processing the liquid melt within that gap region, where there will be a sufficient amount of solid evolved solid already present within the melt, while I mean casting it in the form of components. So, that is the I mean advantage of semi-solid casting. And so, in terms of solid content, although I mean it can be achieved, the high solid fraction can be achieved by mostly it deals with the thixo casting processes, and low solid fraction slurry mostly deals with the Rio casting processes. So, and the I mean also there is another one variant which is called Rio and thixo molding process. So, in all the semi-solid casting processes, the absence of turbulent melt flow during the casting operation minimizes gas pickup and entrapment, because the material is already partially solid. The lower injection temperatures and reduced solidification time also helps to extend the die life. So, in case of Rio casting process, the thing is we generate the semi-solid slurry direct from liquid melt, and so it is a one step process, and after generating that semi-solid slurry we allow it to flow into the die cavity either in the at the onset of gravity, then in that case we call it as gravity die casting, by I mean Rio gravity die casting, or we call it as RGDC. And when we allow the I mean semi-solid slurry to flow within the die cavity at the onset of pressure, I mean using a high pressure die casting machine, then we call it as Rio pressure die casting or Rio die casting. So, I mean so these are the I mean major variants of Rio casting, depending upon whether it is being performed under gravity or under pressure die casting route. So, there are several papers from our research group. I mean if any of you are interested, you can follow. So, I mean in this Rio casting process, molten metal is cooled to the semi-solid state with constant stirring, or it can be using a sloping searing process, or it can be done using a I mean shear cooling roll process, or there are several techniques to generate the semi-solid slurry. And once that slurry is made, what is the slurry is called? So, the slurry has a special non-dendritic microstructure having spheroidal primary grains. Say if I take the example of aluminum alloy, say A356, then it will be I mean alpha aluminum grains, I mean the spherical balls are alpha aluminum grains, and then there is the liquid matrix which is enriched with the rejected I mean silicon, solutile silicon, and then I mean so the stirring or shearing action that is being performed. So, that is basically responsible for heterogeneous nucleation, which is also called copious nucleation, and also dendrite fragmentation. So, because of both of these mechanisms, the I mean this I mean liquid melt I mean gets transformed in the form of specially prepared semi-solid slurry, and then the slurry, after achieving a solid content of say roughly 30 to 35%, then it can be shaped either using gravity die casting when it is called Rio gravity die casting technique, or using a high pressure die casting technique when it is called as RPDC or RDC. So, because the slurry contains no superheat and is already partially solidified, it freezes quickly. So, that is why the solidification time involved in case of Rio casting is also a bit much lower than that involved in the I mean conventional solidification of the same alloy using any of the gravity or I mean I mean gravity assisted techniques, so or pressure assisted techniques. So, now we will be discussing thixocasting. So, thixocasting is also another variant of semi solid die casting. So, what we do in case of thixocasting? So, in case of thixocasting, first we generate the semi solid slurry having non dendritic microstructure like spheroidal primary grains within suspended within the liquid matrix. Even again, if we take the example of a commercial aluminum silicon alloy, which is called as A356. So, then after getting this non dendritic microstructure in the generated slurry, we cast it in the form of non dendritic billet, and so basically we cast a non dendritic billet whose microstructure is like this, and then again we reheat the billet within a heating chamber, and then we, after achieving sufficient reheat, we basically push it again, place it in the short sleeve of the high pressure die casting machine, and then we push it with the help of plunger to push it within the die cavity. So, that is why in this case the solid fraction of the slurry, because we are preparing the semi solid slurry from solid state. So, unlike Rio casting where we are preparing the solid, I say semi solid slurry from liquid state. So, this is the major difference between Rio and Thixo approach. So, Rio is slurry semi solid slurry from liquid. So, liquid to semi solid, and in case of Thixo we are basically achieving solid to semi solid. So, that is the major difference. That is why it deals with much higher solid fraction in the range of 40 to 60% in case of Thixo route, and in case of Rio route we are talking about solid fraction in the range of maximum 30 to 35%. In some cases occasions it is even lower. So, because of this high solid fraction and this reheating of the non dendritic billet, sometimes we also observed liquid pockets within the primary spheroidal primary grains in case of thixocasting. So, that is also detrimental in terms of elongation, and also it causes segregation. Otherwise thixocasting is basically a much costlier process than that Rio casting, because you can understand that once there is a intermediate solidification and again there is reheating, and then there is final casting of the object. So, that is why it is not energy efficient when it is compared to the Rio casting route, and Rio casting is very much close to the conventional liquidous high pressure die casting, and that is also that is why there is having in the large industrial potential of this Rio die casting, Rio pressure die casting technique, and also the Rio gravity die casting technique, and their choice depends upon whether we are going for batch production of a particular component or we need to go for mass production. So, based on that we need to choose between them, but of course, they are superior based on the cost and energy efficiency point of view than thixocasting. And then we will move to the continuous casting process. So, continuous casting process is basically a technique where we generally use the to develop the sheet metals or rolled parts, and you can see that in continuous casting process based on this schematic. So, there is a ladle, and from ladle it goes to a tun dish, and then from tun dish it flows through a mold, and from the mold it is getting solidified, and there is water spray headers, which is, so there is a quenching action. So, that means you can understand from directly from liquid melt we are basically getting the solid, and then also we are doing the secondary processing. Then we are basically directly achieving the wrought form of the particular material involved, and there is several series of rollers involved to achieve the desired thickness reduction of the initial preform, and then also we are reheating, and then we are rolling. So, basically when there is a need for intermediate annealing, that is also we are doing in the process, and then finally we achieve the whether based on the appropriate sheet on demand, we can also club basically the cold rolling and the hot rolling processes with the continuous casting operations, and this is a very much versatile process, and it is widely being practiced in several of the steel industries in our country. You can see it largely being used by Tata Steel. So I mean, so who is one of the largest manufacturer of steel based products in the country. So it is having a wide industrial applicability in that sense. So it is the process in which I mean molten metal flows from a ladle through a tun dish and into a bottomless water cooled mold, usually made of copper, and here cooling is controlled so that the outside has solidified before the metal exits the mold. That means the skin has to be formed and the solidification has to be faster, because after ejecting from the mold it needs to experience the roller, where it can only be useful to do the deformation processing when they have already achieved solidification. So that is why direct water sprays I mean cool the emerging metal to complete the solidification process. So it is a rapid solidification because of high heat transfer involved, because of the water jet that is impinging over the solidifying melt for completion of the solidification, and the solid metal can then be cut to desired length, or since the cast solid is still hot, it can be bent and fed horizontally through a short reheat furnace or directly to a rolling mill, rolling operation. So if the size and shape of the mold are varied, products can be cast with a variety of cross sections and based on the cross sections of the product which are getting manufactured by continuous casting technique, they can be classified as slab, bloom, billet or strand. So there are also vacuum based casting process. So vacuum molding, or which is also called as the V process, prepares molds using dry unbounded sand which is compacted through the application of vacuum. So here the vacuum casting is referred to the mold preparation technique, where vacuum is used as a means to achieve dense molds, where the vacuum process utilizes either a match plate pattern or cope and drag pattern that have all the associated gating and risering system built in. And so because of the application of vacuum to create the compact mold compact, so that is why the molds having much higher green strength can be produced in case of vacuum casting, and there is the chances of leakage of the liquid melt within the mold is nullified significantly, and also it facilitates higher dimensional control of the cast parts with is a much improved structural integrity and reduced surface and subsurface defects. So that is what are the trademark of the vacuum casting process. So in this slide the several different casting mold material and the dyes used for several process casting processes are compared for their advantages, disadvantages and examples, which I have already discussed in detail during the course of this lecture and also before in previous classes. So it is for your ease of understanding and grabbing it into your fingertips. Please go through that. And then so this slide I will discuss, where you can see the there is a comparison made between the quantity and the costs involved. So based on the because engineering is all about, specifically the manufacturing process is all about optimization, the amount of cost you are willing to impart and the desired quality that you want to achieve. So for you can see that as the costs are increasing, you can achieve higher and higher quality. So with a medium cost, semi solid casting emerges as a big player, as a potential manufacturing technique which clubs the benefits of both casting and forging together, and we can basically achieve parts which are having improved microstructure and mechanical properties, which is otherwise not possible to achieve in any of the conventional casting processes, and only superior properties can be obtained in case of forging and to some extent investment casting, but they deal with much higher cost, and that is why their scope is limited to some high value applications. However, semi solid die casting or being the medium cost player, it can largely replace the other existing casting processes. This is the And then finally, we have discussed about several casting processes, solidification micromechanisms, and then we are going to end this by explaining the defects associated. So, there are different kind of defects that generally forms in a cast object. For example, gas defects like which can be further classified as blowholes, scar or blister, as well as pinhole porosity. So, I have discussed earlier about the blowholes when we have discussed about the thumb rules of casting. So, we have I have told you about the bubble damage, about the bubble trail because of the I mean core blows, because of the gas evolution within the mold, because of the organic additives that are being used within the core and also in the mold material, and there and the gases ejects out of them that can create blowholes. Whereas the hydrogen absorption in case of high pressure die casting, it can create pinholes, pinhole based porosity. And number two, different second kind of defects are the improper ramming of the sand causes this kind of defects, which are associated with drop and dirt. So, this is very much needed in case of this happens due to improper ramming, and the possible remedy can be like CO2 molding that we have discussed earlier. So, which can significantly increase the green strength of the mold when we are talking about sand casting, and the resulting solidified cast part can be free from this drop and dirt based defects. And then other problems are cuts and washes, scab, etc. So, so these are the defects that can originate because of improper mold material, and this is again example of metal penetration. This is again because of the improper strength of the mold. So, that is why the melt which is poured within the cavity, it shows a tendency to get leaked within the mold cavity, and within the mold beyond the cavity, and that causes this kind of surface defects, and also it becomes it makes the surface of the cast part very uneven, and it also creates a lot of defects, imperfections beyond the surface, subsurface defects, which can otherwise also be responsible for rejection of the part. So, it should be avoided by any means. And then number 3 is pouring metal defects. So, because of improper pouring, the defects which can originate are misrun, that means improper filling of the die cavity, and also cold shuts. That means there are regions which are left behind, although the remaining regions are filled. So, that cold shut is a defect which is not to be recovered by any other post processing means, and it just forces the component to be rejected. So, that is why you need to be very careful about. And number 4 is metallurgical defects. So, it deals with the preparation of the liquid melt, it deals with the composition of the liquid melt. So, even if the the mold design is proper, the process is proper, if the melt quality is not up to the mark, if it is there, then there is susceptibility of hot tear formation can be seen. This is basically happens due to in case of alloys having a larger freezing window, and these hot tears can also be nullified to a greater extent when we talk about semi solid casting. And then number 5 is mold shift and cold shift. So, this is also I have discussed with you that this generally happens due to if the both the halves of the pattern, both the molding flasks are not aligned to each other properly, the assembly is not proper, then there is a tendency of shift along the parting line, and that can cause severe distortion in the component geometry and forces them to be rejected. So, these are, and then thus there is sand slag inclusion. Again, this happens due to improper preparation of the melt, which can be nullified by starting with a good quality melt, as I discussed with the when I have discussed about the 10 rules of achieving good castings. So, with this we are done with the casting part of the course. So, after this we will be focusing on how to achieve the desired geometry, getting geometry. Although we have discussed in this section of the course that we can also actually arrive at the geometry of the getting geometry by performing analytical calculations. However, in case of complex shapes and in reality in practice, it becomes extremely difficult to to achieve measure, arrive at the required set of dimensions by analytical means, and hence we need to take the help of the numerical techniques that we have discussed in the introduction module of the course. We will be showing you the application of this numerical method to achieve the proper die filling, and also to how to optimize the getting geometry and process conditions to achieve cast parts with desired properties and sound structural integrity. So, thank you for now.